Today I'll be talking about using UE5 to build modern VR action games. So this is me. I've been working on VR for about 11 years. I founded a company called Survios. I'm a CTO there. And we've shipped 7 titles on UE4 in VR at this point across different genres. Our main focus right now is licensing Hollywood IP. So we're migrating to UE5 now. We've remastered our big hit, big hit Creed Rise to Glory boxing game for the new VR platforms in UE5. And we are building this game based on an Alien movie franchise, Alien Rogue Incursion in UE5 from the ground up. It's coming out in December 18, by the way, so please play it. So the target audience for this talk is obviously everyone working in UE5 nowadays. I hope you're all moving it to UE5, not like Valorant that's apparently sticking to UE4 to 7 right now. God help them. But also, obviously, XR, if you're working in VR, this is going to be mostly relevant to you. And then this is going to be a kind of technical talk. So I warned you, hopefully you won't get bored. And when I talk about modern VR action games, I'm talking about some of these kind of expectations from the audience nowadays. So first of all, there's a combination of artificial joystick locomotion and room scale motion. Of course, not every game has to have it, but a lot of the modern action games will have you moving around with joystick, just like modern console games, in addition to being able to just move around the room with your head. Your avatar and the interactable props are going to be physicalized. So if you go and reach with your arm into a wall, it doesn't just go through. All the interactions are also physicalized. There's also immersive object and manipulation. So like when you're reloading a gun, there's multi-stage reload, and you're manipulating the object with your hands and attaching things, etc. And then finally, there's still some care for accessibility. Like even though we're not doing teleport, they're still trying to support like left-handed players and people with different kind of preferences. So my development philosophy is, at a high level, always keep things modular. We have a very modular and plugin based code base, but for the most part, we try to use components as much as possible instead of like really long hierarchy chains. We try to maximize our development efficiency by making sure we can test most of our content outside of VR, just with a VR emulation mode, essentially, with a mouse and keyboard. That way, you're not wasting time just booting up the game, putting it on the headset just to discover that you think just doesn't work, which is like 99% of the time, right? So save your time and make sure you can just play the game and run through it with a mouse and keyboard. Console commands are real useful in Unreal Engine. It's every time we add a new system, we add a console command to disable it. Because that way, if your system breaks something, you can quickly disable it just to make sure, just to see if you're the culprit or not. It's really useful for A/B tests. It's also really useful for if you do want to tune the feel of something when you're in VR, if you expose something when you are testing in VR. So the high-level topics I'm going to talk about today are XR post-tracking, player pawn configuration, interactables, and also input and abilities. So post-tracking. When I'm talking about that, I'm talking about tracking data like your head, your hands, and this is what really makes VR shine. What makes VR special is your whole body is your controller. So we need to have some kind of structure for getting that input and feeding it to other systems. And so Unreal obviously already comes out of the box with a lot of these solutions. You're probably aware with most of them. There's the components, the camera component, the motion control component. There's the blueprint exposed function library, and then there's the the low-level system interfaces that you can access in this, at the C++ level to get the data. So I suggest kind of building your own layer between your game and these APIs instead of just using them directly. There's several advantages to that I'll be talking about. But something to watch out for is for example, the get motion controller data is in world space. We like to cache everything in local space because the systems could be accessing it before or after player movement. And also the OpenXR implementation of get motion controller data is kind of finicky if you have hand tracking enabled. You may need to modify that to make sure you can switch between controllers and hand tracking. So the advantages is it's much easier for you to build a VR emulation layer in between your game and the tracking data for debuggability. It's also going to be easier for you to seamlessly transition from controllers to hand tracking. You'll be able to just switch what transforms you're feeding to your higher level systems, depending on if controllers are active or not, and if you want to. And also, motion controllers are two scene components that you just don't need if you have like a physical avatar. Here's just a demonstration of our emulation of inputs, which allows you to basically press a button and move a mouse around. So it's really useful for just jump in the editor to quickly test to make sure your things work without having to, again, put on your headset. We expose CVARs usually for a bunch of debug visualization. That's another reason that console variables are really useful. So an example of another tool that we've developed for VR emulation is we can save a pose with a tracking pose snapshot console command, and that saves it in i9, so that pose is now available in between editor runs and Pi sessions. So there's automatically console commands that are generated with autocomplete that restore those poses. So it's really useful if you're, again, testing something and you just made some code changes, you can quickly restore it. Really useful for development. One thing to note about emulating VR in a package, the quickest way is you can just launch the game with -no HMD. Like if your game starts in VR by default, you can just use that. And then one thing to watch out for in PS5, mouse is disabled by default. So those are just, okay, hold on. One more thing, height calibration. Usually if you're building a game with an avatar, you probably want to calibrate the user's height. So basically cache the user's height, and then you get that delta from the avatar's desired height, and then you apply that to all your transforms and feed them further down the line again so that no one else has to care about it. Okay, let's move on to more fun things. Those are just the basics, but some devs don't have VR emulation, and I always like to hammer it home because please do not, I know it's counterintuitive, please do not build your VR games in VR. It's just really slow. At least that's my opinion. Anyway, so the way we build our player avatar, so we have a player pawn. We don't use the character class. We build it from the pawn. Gives us more flexibility, and we have two types of components we're attaching to the pawn. The first category is the hand managers. Essentially, those are the ones that have to store state per hand, like logic. So if you're, when you're interacting with something, your left hand and your right hand can interact with something individually. Or each hand can potentially be animating individually. And then there's the everything else bucket, like movement, health, etc. So for the hands, and the reason why I'm talking about this is like in the past we've made the mistake of essentially having like a hand actor and then attaching components to that. That just resulted in just not a very clean structure. It was not very modular, and you just have the overhead of two separate actors. So what's cleaner is just keep everything pawn-centric. You have one component, and that component, each component for each system maintains the lifetime of like two hand objects, essentially. So you could implement this as a UObject subclass, which has the advantage of being blueprint exposed, and other systems can cache reference to it. But sometimes what's cleaner is really actually keep everything is centralized, all the interfacing through the component itself. Like every API, you basically pass an enum for like the left hand or right hand. And internally that class stores the hand data in like a shared pointer or a pimple or ember array. So, modern VR games often will have an avatar or at least arms, and those arms will be physicalized. So one way to achieve that is by enabling updating this flag, update joints from animation. And this is a built-in flag. It's been around since UE4. And what it'll do is it will automatically feed the raw animation pose as targets to the physicalized joints on a character mesh. Once you do that, you want to tune the physics asset. You'll need to tune the angular orientation and velocity drives in your arm constraints. You'll want to probably lower the hand and forearm mass. The lower mass tends to make it a little more stable. Another device that I personally found with inertia conditioning on the forearms, it's something that it's enabled by default. It's something that's supposed to help with long, thin capsules, but for us, it was resulting in actually the arm penetrating walls, so I disabled that. Also, you probably want to enable CCD on the hands so that your hands don't penetrate. I mean, this is not like 100%, but it will, for the most part, prevent your hands just like piercing through the environment. You'll also probably want to add an additional motor constraint between your capsule and your arm and basically feed the target for where the hand wants to go. And this will essentially provide an additional force to force the hand to go where it needs to go relative to a player camera. Because otherwise, the only thing that's driving it are the motors in your arm, which are relative. Of course, you'll want to enable the body simulation of the bodies. You can be simulated from the shoulder down. And for better UX, you'll want to stretch your arms because the avatar arms or even just the IK cannot necessarily reach the user's controller. Maybe the user has really long arms, I don't know, or maybe something's blocking the arm. So to do that, you'll need to stretch. You'll need to update the elbow constraints reference pose and also stretch the capsule so that it doesn't go through things. And here's just a quick demonstration of interacting with a floating red block. Yeah, so obviously all the graphics art here is work in progress, and the game, and this is a dev environment, so no, there's no red floating blocks in the game. But just in case media tries to pick this up and analyze it or something, all the art is not final. This is me interacting with some dynamic props from the game, so they're physicalized. It just demonstrates, you've probably seen this in other games, right? It's not groundbreaking. So finger collision. So there's different approaches to doing this. One approach that seems awesome, but I don't know why, for the life of me, I could never fully figure it out. Is simulating the fingers entirely and basically having some kind of ragdoll of fingers. For us, it just always turns into a spaghetti monster that follows your hand, and that's not very immersive. So we just treat the entire hand as one single unit of collision, and we do that by welding the fingers to the hand. And essentially, when the hand's shape changes, the collision shape changes. We're updating the welded shapes transforms every frame. So you can do it using the built-in method by setting the weld body transform, but watch out that internally, the way Epic implemented it is it actually unwelds the body and re-welds the body. So basically recreating a bunch of shapes every single frame, and your finger's made out of at least 3 bodies, and you have 5 fingers, and you have 2 hands probably. So that's 30 bodies you're constantly welding. So as an optimization, we're just calling set local transform on the bodies. So hand animation blueprints. So we have a component that manages that on the pawn with its own representations, and then we have the animation blueprint. So we're really taking full advantage of blueprint animation linking. This really has helped remove a lot of duplication that we've had to do in the past. We can't use animation layer interfaces because we need 2 of them of the same class, and as far as I know, you can't have 2 of the same layers active at the same time. So instead, we use animation blueprint linking with 2 different tags, one _ left and one _ right. And for each hand, we have an idle hand animation blueprint linked, and that one's responsible for pressing the trigger or the grab and changing the finger the hand pose when it's idle. And then we have this placeholder animation blueprint that doesn't actually do anything, but it's just there to have a tag, so then that thing gets replaced whenever you grab something. And that's really useful because we're able to have bespoke logic for when you grab something, like even a gun, and you can animate the trigger finger with your trigger finger, or any interactable just can define whatever blueprint class they want. So let's move on to movement system. So we rolled our own that is optimized for VR player movement. So the primary responsibilities are not only moving the capsule of the player, but also moving the tracking origin potentially in the player. And the tracking origin is essentially the parent for all the tracking data, like your controllers in your head. The core components that make out the system is the avatar movement component itself, the movement collision component, which is the capsule, the tracking origin, and also a bunch of movement modes that implement this abstract base class movement mode. So the movement modes that we've implemented for Alien are on foot, which is kind of like walking on grounded movement mode, turn in place, like snap turn and such. We also have climb and anchored. I'll be talking about the first 2 today. So the movement mode component, it has an array of movement modes, so these things can stack. The reason why we did that is because we wanted to reuse the turn-in-place logic and just apply it additively to other movement modes. And it's responsible for running the update loop. So initial first phase is poll the tracking state, get that from the tracking polling system. Then it pushes that state to the movement modes. The movement modes calculate the new desired state, return that, and then the movement component applies that, passes that target state to the movement collision to update its tracking origin and its dimensions potentially. So the movement collision component, this looks like a capsule. It's not a capsule, which we made our own primitive component subclass. And the reason why is, well, the primary reason why is I just wanted to put the pivot on the floor. Unreal's capsule's pivot is on the center, which is also sensible, but for movement, it's not as great because the player's constantly standing up and crouching. And our capsule is actually physicalized because we find that it's much more stable when your arms are also physicalized. The capsule is physicalized and they're all constrained together and moving together. You have less jitter and less desyncs because they're all simulated together. And having when you crouch up and down, if the capsule center is at the center, you are actually incurring basically velocity up and down every time. But this way, the capsule center is at the bottom. All you're doing is updating the shape. And we just lock the body rotation lock with the body instance locks that are already available. How am I in time? Great. Yeah, so tracking origin. This is the parent for all the tracking data. This is a scene component. It doesn't have to be a scene component. I love to avoid as much scene component bloat as possible. But it is convenient to parent the camera component to it, which is already automatically updated by Unreal when follow HMD is enabled. So we're kind of using that right now still. So that thing is the movement modes tend to try to move it such that your real head position maintains inside the capsule. So essentially the capsule will move, the tracking origin will move. You're always trying to maintain your body inside the capsule as much as possible. But sometimes you might be blocked by things. So the movement mode interface, as mentioned, this is a kind of abstract base class, and it's responsible for calculating desired transform for your capsule, for also the dimensions, like your radius and half height, and the tracking origin. And at the end of the update loop, since our capsule is physically simulated, we know where we want to go, and we calculate the delta of the position and divide that by delta time. Now you get the velocity. So set that physics body velocity on the capsule, and it'll move to where you want to go in that frame. So the first time around, you might implement this. You may notice that your arms will kind of be like wet noodles following you around as you try to move around with the joystick. So every time you start moving, they'll lag, and then as you stop, they'll overshoot. And that's because the arms themselves are not experiencing any movement acceleration. They're just being physically dragged by their shoulders, essentially. So what you can do is you can calculate the acceleration, which is the delta velocity. So you know what your current new desired velocity of the capsule is. You know what your previous velocity is. Get that delta and add that to the velocity of all the arms and the grab object, and then your things will follow smoothly. Similarly, you'll notice if you're structuring things as we did, and again, sorry if this is the stupid way to structure it, I'm just talking about the hacks that I put in. The first time around when we put it in, our shoulders were lagging behind because the shoulders are constrained to the mesh, to the chest. And the chest is kinematic, right? So the actual capsule gets updated during physics simulation and synced post-physics. So to fix that fact, to simulate the arms together with the capsule, we actually break that constraint and we constrain the shoulders to the capsule itself. And then that has things moving on in sync. So we have this other class called grounded movement physics, and this is like a little black box that we took the code from character movement component, specifically like Oldest API for simulating movement on the floor and such, and we just ripped it out and encapsulated it in this one class. And it's convenient to be able to you can even just allocate it quickly on the stack, give it some inputs, and see where you will be after a certain time. So we can use that for some advanced techniques to predict where you will be, and to see whether you're trying to for example, mantle up a valid location and such. And that's used by the movement modes, all the movement modes to essentially reuse that logic. So, for example, the on-foot movement mode, which is our walking movement mode. And this one has 3 update phases. First is the crouch logic, which updates the capsule half height. It also potentially shifts the tracking origin up and down vertically. It then updates the artificial movement, which is the joystick movement. It moves the collision in the world. And then it finally applies the head motion from your head, moving the HMD. So with crouch logic, there's 2 types of crouch. One is artificial crouch, which is basically you pressing a button, and it interpolates you up and down. So this is an accessibility feature. Not everyone wants to be constantly ducking up and down, or some people might be seating. And the way this works is it shifts the tracking origin and interpolates the tracking origin down. And then the crouch logic automatically updates the capsule height so that the collision height always is at the tip of your head, essentially, your real head. And then, of course, People can also physically duck, which will update the target capsule height. But one thing to watch out for is when they walk into some place with a low ceiling, they might physically stand up. Now at that point, you actually now will be putting what we do is we've shipped the tracking origin down, sort of enforcing an artificial crouch. Theoretically, you could try to black things out, et cetera. Like this is what we do. And then when you come out of that area, we don't immediately just like pop that artificial crouch out. We interpolate it, but we don't interpolate it like automatically. We interpolate it with the joystick movement, which is more comfortable, so that when you physically move your head, you don't suddenly get like a weird vertical movement. It's more comfortable to only combine that with another artificial movement. So finally, we have the head motion. So when you move your head, we try to move the capsule along with you, which will keep the tracking origin in the same spot in the world space. But sometimes the user may be walking into obstruction. So in the case of a wall that is head height, we don't want them to just clip through the environment. So we sweep a sphere at the head level from the capsule to where they want to go. So first we sweep the capsule is blocked. Then we continue sweeping the capsule to where the user wants to go. And once the user gets close enough to a wall, we put this black sphere on the head with disabled depth of material and also like an opening on the other side to tell them they should head that way. If they keep walking that way, we teleport them out by moving the tracking origin out, which will naturally move them out, but we keep the capsule essentially in the same place. And then for lower overhead obstructions like tables, we let them move a little bit further. We know that their head's not blocked. And this is better for UX because sometimes users may be like basically leaning over a table to grab something, and it feels really terrible to just move over something and like you just stop by this virtual capsule. So turn in place, of course in VR you can turn physically any direction you want, but for accessibility's sake, you want to allow people to artificially turn. So the first most comfortable method, turn in place, as most of you will know, that just instantly snap turns you, and then smooth turn is like traditional turn. But then the first, probably when you first implement this with artificial, physically simulated arms, you'll notice, again, lag happening, terrible UX, looks terrible. With snap turn, it's a short thing, but with smooth turn the entire time, it feels like you're, moving through water or something. So you want to correct for this. Our initial attempt was similar to translation, which is try to set the linear and angular velocity. For the life of me, for some reason, I was not able to get this working well. So my fallback was to basically sweep the bodies from the current to the target desired position, and depending on if the sweep is there or not, teleported to either the unblocked position or where the sweep hit. And you really want to do this because particularly with snap turn, you could be snap turning into a wall, and if you just teleport your arms there, then they're going to be inside the wall, and now your arms are stuck in the wall, which looks terrible. This showcase is, I didn't get it perfect yet, but in the game, you don't notice it as much. At least that's what they say. Okay. Okay, let's move on to interactable actors. So the things you pick up in the world, I don't know, maybe this is just my problem, like that keeps me up at night, but I feel like in Unreal, I always have this puzzle of like, I want a hierarchy of classes, but I don't really know if I want a static mesh or a skeletal mesh route. And really, the problem with skeletal meshes is they're kind of expensive. We have too many of them as well. So ideally, you keep static mesh components for your props as much as possible, unless they have to animate for one reason or another, like guns. You could try to use the component override thing that's been added to UE5 now, where like you have a component blueprint, you can select it, you can override the class. You can't make that a mesh component though, because that's abstract, so it has to be a scene component. I don't know. We came up with this like structure that kind of works for a few of our cases. And here I'm demonstrating it for ammo items specifically. So we have a native class and a blueprint subclass of that, ammo item actor native class and a blueprint item actor. And the native class has this reference to a streamable render asset. It's a U property with a meta that restricts it to a static mesh and skeletal mesh. And then once that's picked inside the blueprint, we overwrite the post CDO compiled and just switch what the root component is. I don't know. Maybe I'm like complicating things that don't need to be complicated. But anyway, if you do decide to use skeletal meshes for one reason or another, I highly suggest you turn off ticks when you don't need it. In our case, like a lot of our props, if you're not holding it, they don't need to animate, and they only have one body instance. But one thing to watch out for if you do that, you probably want to modify the chaos sync bodies callback to sync the skeletal mesh to the physics, because skeletal mesh components are normally syncing to the physics themselves in their own tick. But again, if you have a big game with many, many props, you probably want to turn them off. So one neat thing, I think, that we made for Alien is this editor. We subclassed Acid Editor Toolkit and wrote a whole bunch of editor boilerplate. Yeah, this allows us to basically, outside of the blueprint actor editor, have a prop tag the points of where you can grab it and visualize the hand poses. It also has built-in support for visualizing mirrored poses. Essentially, each grip point defines a mirror plane, and it allows you to mirror the hand to the left so that we're not authoring manually like our left hand poses, which would be maddening because every single thing can be grabbed with the left hand. And the hand animations are also mirrored using the animation blueprint node, the mirror anim node. And our each grip point has like grip point tag container, gameplay tag container, and that's useful for queries to determine like what you're grabbing. So you can do gameplay logic to turn on different behavior depending on what you're grabbing, or maybe turn on different grip points depending on tags. So speaking about left-handed support, for some objects you'll actually want to explicitly mirror them, like the objects that aren't symmetrical. So an example of that is a rifle, because the rifle is reloaded essentially by racking the slide, and it would not be a good UX to have to reach around on the other side of the rifle when you're left-handed. So we mirror the mesh by scaling on the y-axis. But if you're building a game with physics, you've got to watch out for one reason or another. I haven't dug myself deeply. There's a line, local to world remove scaling and perform blend physics bones. I needed to uncomment that. The world hasn't exploded, so hopefully I didn't break anything. But that made our case work. But if you also, another thing to watch out for is like, obviously if you have text on your mirrored mesh, now it's going to be mirrored. And unless you're building a game like Alice in Mirrorland or whatever, you probably want to unmirror that text again. So either you want to do a material texture swap, or for like UMG, because there's a separate mesh, separate components anyway, you just inverse or absolute scale them again, because we use, for ammo counters, we use UMG. So, if you're building a modern action game, you're probably holding things with two hands. And again, your first time around, when you just constrain things to two hands, you'll notice that things are not behaving as you expected. You can see a visualization here as I'm moving my controllers around, which are the green spheres. The gun does not quite follow what I'm doing. And here I'm just feeding the direct raw control positions to the physics targets. So what you actually want to do is you want to do, unfortunately, this work yourself a little bit. Normally in VR, the way you aim a gun is you have the aim vector, which is the vector from your primary hand to the left hand, and you have the roll on your right hand. So you want to calculate those targets and feed those to your override, essentially the targets that you're feeding to your physical avatar. And you'll have a much better aiming experience like that. What's next? Awesome, yeah, so some more fine two-object interaction where you're holding an object with one hand and you're doing some other finicky business with the other hand. So this is an example of that with our grenade, which is a skeletal mesh component. And we essentially have this custom skeletal control node that allows you to define through edit inline new what the constraint is. And then there's a bunch of visualization that we're doing that allows you to draw what the range of that constraint is and actually simulate the motion of the hand by clicking it and just moving the gizmo around. Again, a bunch of editor boilerplate. But another way we found handy way of configuring this kind of constraint element positioning is using animations by just scrubbing through them. So this is how we do our gun reload. So we actually have two animations, one for the clip going in and out, and the other one for pulling the slide. And we have a custom anim node blueprint, anim node subclass that references these animations and references the bone that's being moved. And then when the bone that's being referenced is interacted with, the anim node scrubs to the animation when you move your hands. Of course, sometimes you may want to just use physics constraints. I mean, this is probably one of the most basic interactions, but one thing we found is with some of the built-in Unreal things, there's some issues if you just want to use what's out of the box. One is if you have angular constraints, those APIs don't, at least again, maybe I'm wrong, but they don't seem to return anything that's sensible. They get current swing and get current twist. Also, the enabling projection, as even the comment in the engine says, does not really work if you have collisions. So we have our own component that both calculates the current normalized position and detects when you're like basically reaching the limits of rotational position. And also in this video, you can see like if you press really, really hard, the handle starts to leave the hinge. So it starts to like basically break out of its limit. So our component just manually, in the calculation of where you are relative to the limits, will clamp the actual visual position to that, so that you never lose the illusion that the object is constrained to that hinge. We also have these buttons, partially inspired by Half-Life. The ones that you push a lot with your hands, but they're not actually physically simulated. So we're actually using probe collision, which is a new UE5 feature. So it's kind of handy to detect basically like overlaps, but not overlaps. I really hate overlaps. They're really expensive, but with probe collision, you'll get a hit when you're trying to touch something. So this button doesn't have regular collision, it only has probe collision. When probe collision detects that something's going inside of it, we turn on the tick, and then we sweep the button's mesh essentially from its fully pressed position to its idle position. And then depending on where the sweep hits, that's how far we push the button. So that's how we do that. So and another point on interactable skeletal mesh interactables, the ones that have something animated on them that you want to actually have collision on. Again, similar to fingers, you could try to have them as ragdolls, but what we do is we just weld that child to the root body, and that means that the entire object responds to what that screen does, and also it pushes out other things out of the way and such. So again, this is our approach that avoids the complexities of like the constrained body potentially breaking the limits. Highly suggest turning on CCD on your important interactable objects so they don't fall through the floor. But unfortunately, in some cases, it might still fall through the floor. In this example, this floor was just like some artist automatically generated convex collision and totally forgot about it. And then some days later, QA found this. And then some days later, I found it. So anyway, just CCD is great, doesn't always work. And also in general, make sure to try to use bot collision where possible. It's way cheaper anyway. So let's talk about how we manage the collision between the player and the interactable, because everything is physically simulated, and normally your hand pushes the object around, but now when you're grabbing it, you'll want to disable the collision. Now, one basic way of doing that is by, and here I'm showing kind of an artifact, like the first round of implementing it, where you pick it up, and then as soon as you drop it, you disable the collision, and it just pops out of your hand, which is fine, but doesn't look that great. And so the most basic way of implementing this is with a physics constraint, because you're already constraining the object to your hand, and there's already a property to disable the collision. If you do that, though, well, first of all, you'll have that problem, the one I just showed you where the object just pops out. But second of all, like you'll also want to probably disable the collision with your entire arm and potentially like other parts of your body. So in Unreal, they have this tsim callback object that you can subclass. This is kind of like the chaos implementation of the contact modification that we had with PhysX. And this has a bunch of different APIs you can override. But long story short, you can ignore contacts on a per body basis, per pair basis. On top of that, there's some more advanced options like actually getting the target separation of like how much an object is penetrating, and then you can actually modify that. So what we're doing is we actually cache what the separation is, and we interpolate it out when you release the object. And so what that does is it's just a much smoother experience where the object doesn't just like pop out of your hand, more naturally, falling out of your hand. Nothing that's gonna like be amazing for gameplay or whatever, but more immersive. Another thing we're doing is our head has collision. This is just something that grinds my gears, where like I take an object and I just stick it in my face, and like I'm just staring inside of the gun, and no one cares about that, and that's fine. But for me, I just want something more immersive, and like I basically added this collision shape of the head, but you have to make sure to weld it to the physics body, because it's the same issue with like if your arms are attached to your chest is kinematic, so it will be moved out of sync, essentially. So take this collision, well, put it where your face is, but weld it and update its transform when it's where the head is, and weld it to the collision. And that way, when you like hit the gun with your face, your gun doesn't go through your face. One thing you'll notice though, if you're unholstering from your back though, now your gun gets stuck on your head, and that's terrible UX. So what you want to do is you want to modify the world normal. So if your normal is like the opposite of your camera, just like flip it. And that way, as you're pushing the gun into your back of your head, it'll just appear in front of you. So kind of then it's the best of both worlds. And it will never go in your face, and it'll never get stuck on the back of your head. And you can keep smacking your face with the gun. That's the dream. And then hats. Everyone loves hats in VR. One thing to watch out for: hats kind of like a head collision. You want to treat it like that. But on the other hand, hat is a visual thing, and you want to attach the actual hat to the camera, because if you don't, then it's not added to the late update. Late update is a thing that Epic has added 70,000 years ago, which basically updates the visual of the thing that's attached to the camera and the head on the render thread, because there's like a little bit of a lag between like getting something on the game thread, the tracking data, and then it minimizes latency. I'm losing my track here. Where am I going? Okay, input and abilities. So enhanced input, new input framework in Unreal. It's great, except for just as a previous input framework, it didn't really satisfy the need of VR to treat both left hand and right hand inputs as related. Like there's no ability to be like, here's my input, here's my right-handed input, mirror it to the left hand, etc. So we're doing something a little bit different with how we're using enhanced input, because I refuse to manually author duplicate left-handed assets. So we author everything for the right hand, and then our code at runtime at launch basically like dynamically spawns left-handed actions and then binds those actions to the mirrored left-handed keys. And then when the gameplay code needs to get an input action, it basically gets the mirrored action if it knows that the left hand is needed. So the way we use this, for example, is with this ability grant component. And for each ability, we define the ability class and also the input action. And then so all of those input actions are authored for the right hand. So we have this component on the player pawn, and that grants some default abilities like sprinting, crouching, etc. And then we have this component on interactable props. And that dynamically grants the abilities only when it's appropriate. So for the gun, only when you grab the trigger grip. And if you grab it with the left hand, it'll request the mirrored input actions. The other place where we use abilities and enhanced input is for our inventory management, our body slots, or grab slots as we call them. So these are areas in the body you grab with the grab button, and then depending on the ability that's set, it'll activate that ability. So most of them I just grab a couple from body, which goes to our equipment manager, which gives you the item. But we also have like grab ammo, which goes through a slightly different path. And it's just we also have a flashlight, for example. So it's convenient to like essentially abstract the input from what happens using ability system here, and exploit the fact that you can use tags to basically disable things situationally. And then we have this debug input action, and that's going back to my point about making sure that things are testable outside of VR. So like in this case, equip gun is mapped to one key, so we can always press 1 and put the first gun in our hand and not have to like look down and awkwardly grab things of our body. And that's it. I hope you all found this somewhat interesting or educational. Again, thank you for choosing my talk as the first talk to go on this wonderful conference. So again, really appreciate it.